So, students, now we will proceed for the 23rd lecture of transport phenomena. In which we will study radiation energy exchange. Radiation energy exchange. In the previous class, I have told you that in the summer season we are experiencing a lot of energy received from the sun. In the winter season we are experiencing a lesser amount of energy from the sun. That is why we are feeling consequently warmer and the colder seasons. The question is, the sun is receiving its energy all the time in a similar fashion, irrespective of the weather which we are experiencing on the earth. But during the winter season and during the summer season, if you try to visualize the orientation relationship between sun and the earth with respect to spatial coordinates, then you will find that there is some difference. This gives rise to a situation where the quantity of heat energy which have been released from the sun as a radiant energy through vacuum, you are getting some part of that. That part is more in the case of summer season and lesser in the case of winter season. It means if you are talking about the diffuse emitters, that means if the radiation is diffuse in nature, then as per the previous classes I have told you, in the case of rough surfaces, the radiation will be diffuse in nature. That means if radiation energy is incident on a surface, then it will get reflected in so many directions, whereas in the case of specular radiation, you will receive one incident ray, and corresponding to that incident ray you will get a reflected ray by following the law of reflection. That is called the specular reflection or specular radiation, which is possible in the case of extremely fine polished surfaces. So, a question arises that how such things can be quantified, that if A and B are the two objects and A is regarded as a source and B is the receiver, then how the change in the orientation of relative orientation of A and B, how it can affect the quantity of energy released from A and received by B. Definitely, as a function of orientational relationship, this quantity differs. So, in the present class, we will try to understand what is the main factor which stands responsible for influencing this quantity of heat energy received and the quantity of heat energy released from the source. So, basically in this topic today we will study what is this shape factor. Shape factor. So, let us try to have an understanding of this term, that shape factor. So, let us consider surfaces separated by a medium separated when, if I am considering two surfaces separated by a medium and in vacuum and they are at different temperatures, then a net exchange of heat energy will be there. And this magnitude of energy exchange, that will be a function of nature of medium, that is whether the medium is participating or not. So, the medium can be classified as a participating medium or the non-participating medium. So, it depends upon the fact that whether the nature is participating or non-participating, and another factor on which this quantity depends, shape factor. It is also called as view factor. Hence, an understanding of view or shape factor enables us to evaluate the amount of energy leaving a surface and being received by another and being received by the other. That means, this is the shape factor or view factor is the most important thing so far as the assessment of the magnitude of heat energy exchange between two bodies at different temperature are concerned. This view factor or shape factor, it is denoted by a letter Fij. We will denote this shape factor by this abbreviation F suffix ij. It determines the fraction, or first it describes the view factor of surface I with respect to another surface J. This is defined as fraction of energy leaving the surface I and reaching the surface J. This is the meaning of the view factor. So, in cold season or in the winter season, what we are experiencing, that the amount of energy which is being received by the person at earth has a lesser magnitude as compared to that experienced in the case of the summer season. So, this is the view factor which can explain this phenomena through which we are going through all the day and all the season, all the time. So, in order to visualize this shape factor, let us consider there are two bodies. Let us suppose this body is A1. Let us suppose this is another body A2. This is the differential area or infinitesimal area in the A1, which is termed as dA1. This is dA1. This is the normal to the surface dA1, and I am taking another one infinitesimal area corresponding to the surface A2. This is dA2. This is dA2. We treat it as a normal to the surface. This. And this is the another diameter plane on which the center of dA2 is this. They join this the center of this dA1 and dA2. Okay, right? The angle between the center to center, angle between the line joining the center of A1, A2, center of dA1 and dA2, and the angle normal to this dA1, let us suppose this is phi 1. Let us suppose this angle is phi 1, and another, the angle between the line joining the centers of dA1, dA2 and the normal to this dA2, let us suppose this angle is phi 2. Let us suppose this angle is phi 2. So, with reference to the diagram, two black surfaces are there having A1 and A2 as their areas, as well as they are respectively at temperatures T1 and T2. Also, here it is necessary to mention that T1 not equal to T2 and both are greater than absolute 0. Here it is necessary to mention. So, if the temperature difference is there, that means a net exchange of heat energy, will be there. A net exchange of heat energy will be there. This exchange can be quantified by utilizing the concept of view factor, utilizing the concept of view or shape factor. By utilizing the concept of view or shape factor. Now, both the surfaces are diffuse emitters and they are at different temperature. Now, since both the surfaces are diffuse emitters. Diffuse emitters means, as I have told you, that a rough surface is there and some sort of radiation is coming from a source to this surface, is incidenting on this surface, then they will get reflected in so many directions. And that is why I have told you in the previous class, in the case of the derivation of the Kirchhoff law of the black body radiation, that the emissivity and the absorptivity are equal for a black body, and the emissivity or absorptivity of the black body is equal to 1, and every other body have this quantity lesser than 1. So, on those lines I can say you that in the case of diffuse emitters there are so many directions of reflection there. So, it is a possibility that all the heat energy which is being released by A1, that is that emitting the energy in all the directions, because I have given you the concept of the spectral hemispherical emissive power, that is the basic idea behind the hemispherical thing is that let us suppose this is the emitter. Let us suppose this is the emitter from which the heat energy is being radiated. So, in order to take care of all the directions, we are surrounding this surface by a hemisphere. Now, integrating that infinitesimal amount of heat energy which is being radiated from this surface by taking all the directions in view, because you are taking the direction in the 3-dimensional view. So, that is why a spherical hemispherical shape can be designed, because the surface needs to be placed at a place or in the space. So, in order to take care of all the direction, another important term, that is the spectral hemispherical emissive power, is being hypotheticated to take care of all the directions of diffuse radiations. So, since both the surfaces are the diffuse emitters, it means emit energy in all the directions, energy emitted by one may or may not be received, by the other. Also energy leaving A1 and reaching A2, from utilizing the principles of the previous classes, this quantity can be quantified as, that is equal to emissive power of this black body A1 into its area into this shape factor f and f12, that means the view factor of surface 1 with respect to 2, that means this describes the fraction of energy which is being radiated by 1 and received by 2. So, the energy leaving A1 and reaching A2 is equal to this much. Let it be equation number 1. Similarly, energy leaving A2 and reaching A1, that should be equal to EB2 into A2 into F21, reverse order, where this EB1 and EB2 emissive powers of two black surfaces, of two black surfaces. Also, I am keeping this diagram for the time being because it will be required later on as well. So, I am removing this much only. This EB1 can be written as if the value of the Stephen Boltzmann constant here is sigma, and first is that A1 is at temperature T1. So, this will be equal to EB1 equal to sigma T1 raised to the power 4. Let it be question number 3. Similarly, this EB2 equal to sigma T2 raised to the power 4. As the surfaces under consideration, are black in nature, it implies all the incident radiation will get absorbed. So, the net energy exchange in the case of finite area, net energy exchange, it is abbreviated by capital 1 to 2, that may be given as EB1 A1 F12 minus EB2 A2 F21, that is equal to sigma T1, sigma common T1 raised to the power 4 A1 F12 minus T raised to the power 4 A2 F21. Let it be question number 5. If both the surfaces are the same temperature, if let us suppose the temperature of A1 and temperature of A2 are same, what will happen in this case? If the same temperature, they are on the same temperature, that means there will not be any heat exchange. So, if the condition is, if both surfaces are same temperature, are at same temperature, then what should the value of Q12? That should be equal to 0. It means as per the expression number 5, so as per the expression number 5, the value of Q12, so the value of Q12 If the same temperature is there, then T1, T2, that is sigma T1 equal to T2, that is, let us suppose equal to T1, sigma T1 raised to the 4 into A1 AF12 minus A2 F21, and that should be equal to 0. Now, since T1 is greater than absolute 0, that I have assumed earlier, and the Stefan-Boltzmann constant is also not equal to 0, hence this needs to be equal to 0. So, it gives rise to A1 F12, that is equal to A2 F21. This is an important relationship in the shape factor algebra, denoted by the equation number 6. This equation number 6, this is called the reciprocity relationship. In shape factor algebra. In the next class, we will understand what are the different algebraic rules regarding the shape factor, and this is an important relationship in that context, that is the reciprocity relationship. Now, let us try to understand what is the geometrical viewpoint of this view factor, and how a generalized expression in that case can be made. Let us go for the generalized expression for the view factor. Let us start from here itself. Now, coming to the next topic, or suppose to the last topic of the today's class is the generalized expression for the shape factor. Generalized expression for shape factor. Now, with reference to this figure, again I am utilizing the same figure. With reference to the above figure, dA1 and dA2 are two elemental surfaces separated by distance r. This distance here separated by a distance r. This r can be defined as center to center distance between two elemental areas. And what about this phi 1 and phi 2? Phi 1 and phi 2 are the angles between r and normals to this area dA1 and the area of this dA2, and normals to elemental areas dA1 and dA2 respectively. dA1 and dA2 respectively. This is also called as polar angles, as we have gone through in the case of polar coordinate geometry, also called as polar angles. Now let delta q 1 to 2, delta q 1 to 2 is the amount of energy released from dA1 and reaching dA2. So this is defined as see, for the expression that I am going to write for the delta q 1 to 2, that will require the idea about the relationship between the amount of energy exchanged and the emissive power. For that, it is advisable here, because the course of this transport phenomena is very large, and within a short period of time or even in the online mode, each and everything may not be completed amid this pandemic situation that is prevailing in our country. So it is better to understand that relationship from a book that I would like to refer here. Please go through the book Heat Transfer by S.K. Sohm for the derivation and understanding of that relationship, that is the relationship which is existing between the delta q 1 to 2 and the emissive power. So here, because I am referring the book and you have to go through that book, so it is better to write the expression right straight way. So this is, please go through that book for the clearance for that. So that is given as I1, that is the intensity of radiation, into dA1 cos phi 1 into from 1 to 2. Solid is subtended from surface 1 to surface 2. So that will be given as, this quantity is given by EB1 divided by pi, this quantity is dA1 cos phi 1, and the value of the solid angle, seen from 1 towards 2, that is given as dA2 cos phi 2 divided by r square. During the JEE preparation, you have also gone through these things, especially in the case of Gauss law of the electric charge. There is a concept of solid angle, that over the entire surface you can assume the solid angle is equal to 4 pi. So this can be written as EB1 into dA1 cos phi dA2 cos phi 2 divided by pi r square. So it can be given as EB1 cos phi 1 cos phi 2 dA1 dA2 divided by pi r square. Let it be question number 6. No, let it be question number 7, let it be question number 8. So, the expression for infinitesimal energy exchange between 1 and 2, that is this. Similarly, in a similar fashion, amount of energy leaving dA2 and reaching dA1 can be represented mathematically as delta q 2 to 1, that should be equal to EB2 cos phi 1 cos phi 2 dA1 dA2 divided by pi r square. Let it be question number 9. So, the net energy exchange, now you can remove this diagram. Now, so the net energy exchange infinitesimal. So, the net energy exchange, that is delta q net 1 to 2, that should be equal to this expression minus this expression, that should be equal to minus EB into cos phi 1 cos phi 2 dA1 dA2 divided by pi r square. Let it be question number 10. So, for finite surfaces, A1 and A2, that has been shown in the diagram, A1 and A2 net exchange of energy can be given as, how it can be given as, you have to integrate this quantity over this area A2 and A1, so that can be written as Q net 1 to 2, that should be equal to EB1 minus EB2. This is a constant quantity. So, double integration cos phi 1 cos phi 2 dA1 d2 dA2 divided by pi r square. So, here A2 over this area A2, then over this area A1. Let it be question number 11. By taking the help of equation number 5, it can be inferred that integration in the RHS of the equation number 11, must corresponds to either A1 F12 or A2 F21. That is clear. So, this quantity, that means this quantity a1 f12, that should be integration over the a2 a1 cos phi 1 cos phi 2 dA1 dA2 divided by pi r square, from where the generalized expression for the shape factor f12 may be deduced as integration over a2 integration over a1 cos phi 1 cos phi 2 dA1 dA2 divided by pi r square. Let it be question number 12. Let it be question number 12, and similarly it may correspond either to a2 f21. So, a2 f21, that should be equal to integration over the area a2 followed by integration over the area a1 cos phi 1 cos phi 2 dA1 dA2 divided by pi r square. So, the expression for f21, that is a fraction of the heat energy released from the surface 2 and being received by the surface 1. So, the f21, that should be equal to integration over a2 integration over a1 cos phi 1 cos phi 2 dA1 dA2 divided by pi r square. Equation number 12 and 13 are the generalized expression of the shape factors. You have to utilize such equations in order to evaluate the shape factor for different geometrical conditions. In the next class, we will try to understand that how the shape factor can be calculated by utilizing either this equation number 12 and 13 for the different situations. Thank you.